Now we need to talk about how it is that we want to have protons and neutrons interacting with each other to build and bind themselves into a nucleus. And to do that, we have to discuss how forces work in general in quantum field theory that we're going to do not very accurately, but we need some information to talk about how to do this. So in quantum field theory, and we'll use this as an idea for what happens in general, if, say, we have the electron bound to a proton in a hydrogen atom, we can describe the most fundamental interaction between the electron and the proton using a Feynman diagram that looks like this. So there's an electron coming in, an electron going out. So label that E minus. The fact that I use a straight line with an arrow, it kind of indicates which way the particle is going and what kind of particle it is. Likewise, I can have a proton going and proton going out. And in between, I have a squiggly line that I'm going to label as a gamma. So this all represents the fact that the fundamental interaction between an electron and a proton by the electromagnetic interaction involves the transfer of a photon between them. And in fact, that this happens only at one point in each case where the electron goes and it emits a photon, and that photon then goes and hits the proton, and we can express the force in that way. At these junctions, they each have a strength given by the electric charge E, which includes how likely it is for that to happen. And you'll see there's two of them, so when we calculate this whole process, we're going to have an E squared term. At this intersection as well, where the nodes where things come together, we have to conserve things like charge is conserved and angular momentum is conserved and momentum is conserved. All our conservation laws happen at these points, so that we can only understand forces at the fundamental level by drawing these sort of diagrams. Now, often people talk about how, okay, time goes in this direction and momentum goes in this direction, and that's true, but this really describes a term for when you're scattering electrons off protons. You have to do a big calculation. There's an integral involved of all the possible ways the proton can interact with the electron. And in that integral, in the integrand, there'll be terms that look like this. And in fact, this is the only term there will be, but there will be complications of it that are, you might have multiple copies of this. So in fact, at low energy, we might say that this looks more like, we have an electron going along this way and a proton going along this way, and they just have a continuous stream of photons going back and forth that binds the electron to the proton, or that interact over time in a Rutherford scattering kind of experiment. Now, in this calculation the calculation that this represents, it's important that the photon is massless, because that controls how far away it can go and what kind of energy momentum conservation we can have. Then, so because the photon is massless, it can go much farther, and we'll talk more about that in a second. By the way, the approximation when you have electrons scattering off protons at high energy, where only one photon is exchanged, like the approximation is good that all the interaction happens with one photon, that's called the Born approximation, and it's used in high energy physics a lot. Mostly in this case, I introduced the Feynman diagram for the electron-proton interaction to indicate the kinds of things you can do and the way that interactions work. It's a way to think about what interactions can happen. And then we will go on and say, okay, now let's think about a proton interacting with a neutron. And so we want the same kind of interaction possibilities. Here we're going to have a proton. Here we're going to have, it's going to continue to be a proton, a neutron, and a neutron. And we can do the interaction by having them exchange some kind of particle, which I'm going to call a pi. Now, because the proton in this diagram remains a proton, the charge is constant there. The thing that's exchanged has to be a neutral particle of pi naught, and that works with the neutron as well. I could then draw similar diagrams where I have a proton coming in and a neutron coming out, and interacting with a neutron going in and a proton coming out, in which case I've exchanged, have to keep the charge going, so this is going to be a pi plus, and we can follow then the charge, because at each intersection the charge is conserved, so the one plus charge goes here, then it goes here, and then it goes there. It left nothing here, and it started with nothing there, so we have the neutron. And likewise, there's one more picture like this. We can have proton, well, let's switch them. Neutron, proton, pi minus, going to proton, neutron. So it turns out that if we want to do this, then we can have a massive particle, the pi naught goes through there, and then we can ask what kind of mass do we expect it to have. Another way of saying this is that if you have a proton coming through at a given energy, it can create this pi naught, but that takes, if that has mass, then that creates energy, and the energy is not conserved. It's okay if the energy is not conserved, because we know from Heisenberg that delta E, delta T can be of order h bar. So we're free to violate conservation of energy as long as the time is short. And in this case, we can generate energy, which is the mass of the pion, but only on short time scales, and that means it can't get very far, so the range of the interaction is reduced. Okay, so now if we talk about the binding energy, or what kind of potential, like the Coulomb potential, we know would be created by photons that are massless, but what kind of potential would we have for photons? And it's hard to do this with the Schrodinger equation, but we can do it with what's called the Klein-Gordon equation. So let's talk about quantum mechanics at that level then. And so recall that the Schrodinger equation has the form I h bar d psi dt equals minus h bar squared over 2m Laplacian of psi plus potential of psi times psi that's the Schrodinger equation, and it comes from the non-relativistic energy equation. This represents the energy. This represents the kinetic energy in the form of p squared over 2m, and this is the potential energy. So we have kinetic energy plus potential energy is the total energy. But that's not a relativistic equation. But in relativity, we have a similar equation where we know E squared is P squared plus M squared, where I've now used C equals 1 frame there. So if I convert that into a quantum mechanical picture, I can, rather than having E, I will now have E squared. And so you have minus h bar squared. The minus sign comes from I squared, d squared psi dt squared. So each energy corresponds to a time derivative. The momentum, I'm going to drop the p part of it, but is minus h bar squared Laplacian, which is the spatial derivative squared, psi, plus m squared psi. And this is called the Klein-Gordon equation, and it is a quantum mechanical equation like the Schrodinger equation, but one that takes special relativity into account. So it's a relativistic quantum mechanical equation. Now, if we look for solutions to this equation that are static, so in fact, let's set this equal to 0, because if we have d psi dt equal to 0, we want static solutions to this. We can try to see what happens in this case. And so let's do that first. So static solutions. To the Klein-Gordon equation should have the form of Laplacian of psi equals m squared over h bar squared psi. Okay, so in electromagnetic interactions with a photon that's massless, so in which case m equals 0, now you have del squared psi equals 0. Well, this is just the Poisson equation. We know that if we have psi, if we have a potential of r, which we can equate to E times psi of r, and that if this equals minus E squared over 4 pi epsilon naught times 1 over r, that this is a solution. We should note that, so for spherically symmetric equations, del squared in spherical coordinates is 1 over r. The way you write it in spherical coordinates is 1 over r d squared by dr squared of r times f, where the f is here as well. So if you have some function in spherical coordinates that is also only dependent on the radial coordinate, and you take the Laplacian of that function, this is the only term that you have. And so you see that for the electromagnetic case, the RF, this R cancels and you have a constant here, so that if you take two derivatives of it, you get 0. Okay, so what about the case with a massive boson? Well, it turns out that we can write a different equation then. So again, I'm going to rewrite some of that. So we're looking for del squared psi is m squared over h bar squared psi, where m does not equal 0 in this case. What we want to try is a potential of the form g squared, some other charge, over 4 pi. The epsilon naught got put into the e, or the g part. We still have the 1 over r part, but we add this exponential factor, e to the minus r, over some constant, capital R. Well, let's calculate then what the Laplacian of v is in this case. Well, it's 1 over r d squared by dr squared of rv. Well, the r here cancels this r here, and then we have the v. We have two derivatives with respect to r. They bring down 2 minus capital R's, and so, and then we put back in the little r, and so this equals 1 over r squared, 1 over r g squared over 4 pi e to the minus r over r. And we can rewrite that. That's just 1 over r squared v. So we see that if we then plug back in, we're going to have 1 over r squared v is m squared over h bar squared v. And therefore we have that r must be h bar over m. Okay, so with a massive photon or a massive particle doing the relaying the force from the proton to the neutron, we find we can have a potential of the same form as the Coulomb potential, 1 over r, but it has this exponential cutting off factor, and the range at which it's cut off is given by 1 over the mass and h bar. And so what is that range? Well, recall that h bar c is 197 MeV Fermi. And so if we plug in a c here, so h bar c over m c, I'm not going to worry too much about the c's except for the upper part, but then we need to have, so m of order 200 MeV for a range of 1 Fermi. Turns out the nuclear range is slightly bigger than 1 Fermi, so we're going to want a pion mass that is somewhat less than 200 MeV, but 200 MeV gives the right order of magnitude, significantly smaller than the mass of the proton itself, 200 MeV being about 1/5 of that. And so that's how we get the mass of the pion. This, by the way, this potential here, it's called the Yukawa potential, first written down by Yukawa in the 1930s. Now, we should point out from that that the remarkable thing about this interaction, this potential, is that the neutron and the proton, they're really almost identical. In other words, in this Yukawa potential, the neutron and proton stick to each other or interact with proton-proton interaction, or the proton-neutron interaction, or the neutron-neutron interaction, are all the same, independent of the charge, whether it's a proton or a neutron, that you have. This is called charge invariance, and so all the interactions look like this: N or P, N or P, P or N, P or N, pi, plus, minus, or 0. Describes all the interactions, and we call this charge invariance in nuclear interactions. Now, the fact that, and of course the neutron and the proton also have almost the same mass, to about 1%. Their mass is the same. The only difference is really that the proton has a charge one more than the neutron in terms of the fundamental charge. We can make an analogy here with spin. If you have an electron that's spin up or spin down, we usually think of those as being the same particle in two different states. But if we think about, filling the shell of the lowest level of a hydrogen atom with 2 electrons, we know they can't be in the same state. So we need a spin up and a spin down. But we could say that we just have the 2 different particles, which are kind of the same particles filling in there. So in this analogy, we want to make neutron and proton 2 different types of the same particle. And since there are 2 of them, we think that that should be like a spin 1/2. And in fact, we're going to come up with something called isotopic spin or isospin to describe this. So rather than, so if we had, for regular spin, we can have h bar over 2 spin up, or h bar over 2 spin down. States, that's one way to describe it. For regular spin, for isospin, we have the states Pn, right? So in other words, we can have the proton being the 1, 0 state and the neutron being the 0, 1 state, like that. Two different projections of this esoteric isospin vector, which can be projected either into the up state, which is the proton, or the down state, which is the neutron. So with all that, and I should say then the pion as well then can be thought of as a isospin, total isospin equals 1 state that has a projection +1, 0, and -1, which map exactly onto the pi plus, pi 0, and pi naught states. Then we can go on and describe what is the approximate nucleon-nucleon potential that we have. And so for that, we're going to draw a picture. So if we have R and a potential, what we need to have, so the proton and neutron interact, but they don't collapse into the same point. So we need to have a repulsive potential, then an attractive potential, and we can treat it pretty much as a square. It has a radius of R, whatever that is. It has some potential depth V0, and it has some very small size repulsive core delta. Now, for nucleons in a nucleus, the energies are actually pretty low. We will not probe the size of this delta here, but it's necessary if your vision of protons and neutrons in the nucleus is of little magnetic balls that stick together but don't collapse into each other. The fact that they're balls that they're rigid balls that you can't overlap, that's the delta part. But that mental model of balls going together doesn't quite work because their delta equals R, not being much smaller than R. But in the same way, it does keep it from collapsing. Now we should note that for the neutron, or for the proton-proton case, for the proton case, we have to take into account the electric field as well, the Coulomb potential. And so if I start out with something that looks like this, I want to add to that this Coulomb potential. And I should remember that the Coulomb potential, as they get close to each other, scatters out because at the center of the charge distribution, you don't see any of that charge distribution. When we add all that to the proton potential, we're going to get something that, in fact, looks like this. And so, if I now erase this part, we see that, in fact, for protons, there's a potential barrier of a given size, so that if you had a particle coming in with a given energy, E0, it could only get to some minimum distance from the core and would be repelled. But if it had enough energy to tunnel through that gap, or it possibly could tunnel through that gap, or if it had enough energy, it could end up bound inside this potential. We'll move on from there next time to talk about how we can model the whole nucleus, not just nucleon-nucleon one at a time interacting.